Yeah, here we go. So first of all, our first speaker this morning is Fabio Del Sordo. He got his PhD working with Axel Brandenburg at the University of Stockholm and Nordita. Since then, he's worked as a postdoc at Saclay Paris, Yale, and the Institute of Astrophysics Crete, and has recently moved to the Astrophysical Observatory of Catania in Italy. His research has incorporated a number of topics, including light curve analysis and exoplanet detection, and he's currently a member of the European Plato mission. On top of this, he's a co-founder of an international research initiative, Galileo Mobile, which aims to bring astronomy to underprivileged communities. And he's also, I assume, the first hot air balloon pilot we've had as a speaker. So I'll hand it over to Fabio for his talk.
Thank you very much, Rob. Thank you, everybody, for attending. It's a pleasure to have the opportunity to give this seminar from overseas. Actually, COVID allowed me to do that. Otherwise, I guess I wouldn't be able to do that. But okay, it's one of the few perks we get from this global pandemics. Yeah, I'm going to give some updates about our closest neighbors, so the Proxima Centauri system. And work I'm going to present was done entirely together with Mario Damasso from National Institute of Astrophysics in Turin. And then the core of that also with a number of other people that I will enumerate later. So Proxima Centauri, this is our closest star. It belongs to a system of 3 stars, Alpha Centauri A, B, and this is the smallest star in the system. This is an M dwarf, mass more or less 0.1, 0.12 mass of the Sun. So it's fully convective star. Means it's one of those stars that are quite active and whose lifespan is quite long. And one feature I'm presenting here in this slide is the demonstration that it has a rotational period of about 83 days. But okay, it's likely has a feature of differential rotations, as we will see later. So I'm going to talk about the planetary system hosted by around this star. And first planet was discovered 4 years ago by Guillaume Andrade-Escudé and a number of other people, which basically made use of high cadence observation with HARPS, and they detected the planet orbiting in about 11 days with an amplitude, so in radial velocities with an amplitude of about 1.3, 1.4 meters per second, and an eccentricity that is not really constrained. Now, importantly, this planet was, the detection was very solid. Along with Mario Damasso, we used the same data and we confirmed the detection by using a different method. I will explain this later. But importantly, the planet was confirmed also this year by a team led by Suarez Mascareño, which used another spectrograph, Espresso. And with Espresso alone, they were able to basically retrieve the same orbital period. And this picture here shows exactly the result got and published by Suarez Mascareño in Astronomy Astrophysics this year. So the detection of Proxima B is quite solid. And of course, throughout the years, people have been asking if other planets may be present in the system. And so they start putting upper limits on planets. So some came from astrometry. And for instance, a number of authors excluded the presence of a Jupiter mass planet in between 0 and 0.8 astronomical unit. I cannot see my own slides. Okay, and then they put some other limit, like 1 sigma mass upper limit on 0.3 Jupiter mass planet, up to 10 astronomical unit. And a number of other work, and also Proxima b was widely studied, and conclusion so far is that it is not a transiting planet. This means that this gives some constraint on the orbital inclination of all the possible planets we can find around Proxima. New data, of course, keep coming, and in particular here I'm showing data from a Red Dot campaign, which we used for the results I'm going to present. And these are 60 additional radial velocities collected in 2017. But beside this, we also made use of re-extracted radial velocities, both with HARPS and with the UVES. And this was work done by Butler and collaborators. And this is published in APJ. So this means that, as you can see in this plot, there is a new, this is indicated by this red arrow, there is a new chunk of data that can help us to constrain and to inspect this planetary system. So what we did was to use a model that we used also in 2017, based on Gaussian processes analysis in a Bayesian framework. And this led to the detection of proximal rotation in radial velocities. So this is quite important, mainly for two reasons. First, because one could could make use of a model to understand the stellar noise present in radial velocities. And then also in a wider sense, it's important because the effect of the rotation on radial velocities is not really understood so far. So for some stars like Proxima, it's possible to retrieve the stellar rotation, but this is not true for all the stars. And what we use is a model that is based on this kernel that is shown here in this formula, where a number of parameters are used. So there are some instrumental offsets, instrumental jitter, but mainly there is a quasi-periodic, the core of the kernel, if I may use this expression, is a quasi-periodic model that is based on the amplitude of correlations and correlation decay time scale, lambda, stellar rotation period, theta, and then a length scale of periodic component, omega, or W actually in this formula. So using this on the radial velocities, actually we could see that we could retrieve quite well the rotation. And also importantly, the presence of Proxima b led us to use this model to fit the radial velocities with one Keplerian orbit, that is that of Proxima b. And then we could extract the value of these parameters that are listed here. So by doing that, we could then have some residuals of our analysis. And then from that residuals, we could do some basic analysis with periodogram, which is shown here. And this is really a basic periodogram, a global long scale periodogram that we use on this data set, on these residuals. And then we see that a signal with a period of about 1900 days pops up. So of course, when a signal that goes beyond Farsalan probability and there's a p-value quite high, or quite low actually in this plot, we should understand what is the reason for having this signal in the data. And I will show that according to our analysis, this is indeed a planet, Proxima C. And so doing the Keplerian fit, what we get is that a planet well explained this signal, this periodic signal. So Proxima C, the second candidate planet in this system, should have a mass that is 5.8 the terrestrial mass, a period of about 5.2 years, and then a signal that is 1.2 meter per second. This means two things mainly. One, that the planet should have also a quite remarkable maximum angular separation, and then some minimum astrometric semi amplitude. It's also quite large. And it also means from the signal that it is only relevant at the 3 sigma level. So this makes the signal solid, but not really bulletproof, I would say. That's why the planet, it is still a candidate planet. Here I just show a bunch of parameters we derived in the discovery paper. In particular, I want to say that all we got is in the approximation, is the assumption that the eccentricity of the orbit is 0. We made some attempt also leaving eccentricity as free parameters, but we could not really constrain that. So we left it as 0 value. And we also are able to retrieve, of course, the orbit of Proxima b quite well. Here I go to show that with this plot on the right, the Proxima C is actually it's going to it lives in a space of the planetary of the parameter space, in area of the parameter space that is quite empty, and indeed there's among the planets discovered on long orbital periods with radial velocities. It is the planet with the minimum mass. And the main reason is that this planet is really complicated and expensive to discover, because one needs really a high number of observations to get it. But this makes it also a bit special, I would say. But of course, while studying this signal, we also asked ourselves if the signal could be related to other physical phenomena, and in particular to an activity cycle. So we made use of an extended photometry with coming from NASA's telescopes, and we did a fit with. We tried several fits, but the one that is presented here is with 2 sinusoids basically, and one is to fit the rotation and one to fit the magnetic cycle that was discovered by Vargelin et al. In 2017. And so we see that actually this signal is quite different from the signal we found in the radial velocities. The difference is quite relevant. And so this leads us to think that there is no correlation between the 2 signals. And we also made use of activity diagnostics like H-alpha index, and calculating the correlation between alpha index, H-alpha index, and radial velocities, both in case of only ARPS radial velocities and UVES and ARP radial velocities. We see that the correlation between the radial velocities and the activity index is really low. So this leads to us to think that there is no correlation and the activity is not responsible for the signal we discovered. But of course, we want to examine also some perspectives with other velocities, because we could ask ourselves, is it possible to really confirm in a robust way the existence of this planet? So Mario and myself, we envisioned a kind of experiment with simulated radial velocities. We created mock data sets with radial velocities consistent with the characteristics of the data collected with various instruments. We analyzed them with Gaussian processes, and we built some figure of merit to see whether or not they could confirm or disprove the existence of the planet. And we created two sets of, we wanted to answer two questions. If Proxima CSE exists, then it should have an imprint of radial velocities. And is this, which observational effort do we need to confirm it in the next 5 years? Of course, we said 5 years, more or less, as a time span, because it more or less corresponds to one orbital period of the candidate planet. On the other hand, we also asked ourselves, if the planet does not exist, is it possible to disprove it, to disprove its existence in the next 5 years? So the short answers are, in the first case, that the detection can be improved, but only up to a 4 sigma level. On the other case, the significance of the signal can go down to a 2 sigma level. So in this sense, we say that we cannot really have a strong answer from radial velocities alone. Of course, the longer answer here, I took a couple of tables from the paper we published in Monthly Notices this year. And so we created a number of data sets, and we built some figures of merit. Here there are listed in the table, but it's just to show that we did a number of experiments, and in more or less what we see for the first question is that the significance, you can see it here on this on the sixth row on the right part of the table. We see that the significance more or less is around 3 sigma, between the 3 and 4 sigma, and there is some improvement that we can expect in the next year with various simulated data sets. For the problem 2, instead, we see that the significance can go down between 2 and 2.4 sigma. The takeaway message from these simulations, from this exercise, it is that we did also to try to plan further future observations, radial velocities observations, is that it is better to spread the observational effort on a long time span rather than concentrate it on a short period. And this is likely because the planet has a long period, orbits on an orbital period. There is some dependence on the prior that we use in our Bayesian model. And this is something that could be worrisome if you want, because solid results should not depend on prior, but anyway, it is expected for such kind of signal. And we once more demonstrated long period and low mass planet investigation is not really sustainable with spectroscopy, so it's unlikely we could discover a high number of planets with this method in that part of the parameter space. But also, we selected 5 years as a time span because we predicted in the discovery paper that Gaia is able to confirm the existence of the planet with its final data release that should arrive before 5 years. We don't really know when. At least Gaia should not be really affected by coronavirus. And this is indeed a plot from our discovery paper. This is about the results that Gaia could bring us, and this is simulated observations that include astrometry alone, or radial velocities and astrometry in red. And this is a plot of the true mass of the planet versus the orbital inclination. And we can see that if the planet is there with this quite large astrometric signature, Gaia should really be able to see it. If it doesn't see it, means that most likely the planet is not there, and there is some other mysterious reason for that signal. But thanks to the fact that actually the planet is on a quite large visual and physical separation, more than 1 arc second from the star, from its parent star. And thanks to the fact that in 2017, a group led by Guillermo Anglada, that is not Guillermo Anglada Escudé, but it's another Anglada, detected some mysterious object or signal or feature, I would say, with ALMA around Proxima. We wonder whether we can do some imaging of this planet. So we have a ALMA proposal accepted, the DDT, but we couldn't observe it because it was accepted only this year. And here in this picture we show, these are taken from the paper by Anglada in 2017. They proposed some architecture for this system, and you see on the right, in the right panel, so around the central source that is Proxima, on the bottom left, there is some feature that could be consistent with Proxima C. Although, okay, we predict that it should not really be visible with ALMA, but we don't really know how the planet is. What are the characteristics of the planet?
Sorry to interrupt, just 2 minutes, please.
Yeah, I'm almost done. So we can also ask if we can see it with sphere, and we got in touch with the people working with the sphere data at the University of Institute of Astrophysics in Padova, led by Raffaele Gratton. And we were lucky because they observed Proxima when the candidate planet was in quadrature according to our orbit. It was in 2018. And so when it is in quadrature, actually, we know that the real separation in the sky should be consistent with the maximum angular separation. And there is some signal that could be consistent with Proxima C. So they did some prediction for the orbit, and they made here 2 cases, elliptic orbit and circular orbit. And the blue dots are the detections in terms of signal to noise. So the darker blue is higher signal to noise. So the planet may be visible also with sphere. We couldn't observe it for also due to COVID later on, but so we went forward and published some results just to make sure that the community knows about this possibility. And this planet may be also observable with sphere. So just to conclude, some follow-up and perspectives, there have been also attempts to measure mass and orbits by Kervella, by Benedict and MacArthur, which measure the mass of 7 plus or minus 1 terrestrial mass by combining radial velocities, Hubble Space Telescope, and sphere observation. Very nice work. And also, I like to read this paper led by Alvarado Gomez about the characterization of the Proxima C space weather. But okay, first I want to, I would like to see the confirmation of the existence of the planet. Although this work, I really liked it, and they predicted that there should be Earth-like stellar wind conditions. And that's all. Thank you.
So thank you, Fabio. Does anyone have any questions? They can feel free to use the raise hand icon or perhaps post their question in the Zoom chat. While we wait for those coming in, I just have a quick question. So how different is the orbital inclination to Proxima B? Is it similar or is it completely different?
Oh, well, we don't know. We don't know, but we assume that if we can measure one inclination, they both have similar inclination.
Yeah, I see.
Yeah. According to this work by Raffaele Grattone, should be more or less 45 degrees.
Do we have any more questions? If not, I will pass over to Sirio, who will introduce our second speaker. Thank you again, Fabio.
Thank you.
Okay, thank you. So let's move on to the second speaker. So just a reminder, we are recording the videos and they will be posted on YouTube. So please let us know if you dislike that. Our second speaker is Allison Matthews, who is a graduate student at the University of Virginia, working with radio data, trying to explore questions of observational cosmology. And today she's going to talk about determining the star formation history of the universe using radio continuum measurements. So please, if you have questions, you can write them in the chat during the talk or raise your hand at the end of the talk. So Allison, can you share your screen and go ahead.
All right, so hopefully everyone can see my screen.
Yeah.
Before I get started, I just want to say hi to a few friendly faces or friendly names that I see on the participants list. 6 years ago, I was an REU student at the CfA looking at stellar evolutionary models with Willie Torres. And so I don't know if I could be talking about something more different than that right now, but it's fun to be back in a way. So, okay, anyway, I'm going to be talking about a radio continuum measurement of the star formation history of the universe. And of course, I have to thank my advisor, Jim, along with a few other people who made this work possible along the way. Okay, so cosmic star formation history. This tells us a lot about galaxy evolution. It tells us when most of the heavy elements in the universe were formed, and when most of galaxies assembled their stars. So if you've heard a talk about star formation, at higher redshifts at least, you've probably seen something like this plot. It's showing the star formation rate density as a function of redshift. And you can see that it all peaked at about 2, redshift of 2, something we call cosmic noon, and it's been declining exponentially ever since. So you need 2 things in order to measure the star formation rate density, naturally a star formation rate and a distance. So in terms of the star formation rate, you want to be looking at a part of the spectrum that corresponds to short-lived populations like massive stars. So massive stars emit primarily in the UV, which means that UV observations directly probe the star formation rate. But unfortunately, they're highly affected by dust obscuration. And to make matters worse, if you looked at a plot of the dust attenuation with redshift, you'd see that the dust attenuation peaks at a redshift of 2. So at the time where most galaxies are forming the bulk of their stars, it's also the time where UV measurements of that are the most uncertain. So you could turn to the far infrared, which is just the re-radiation of that UV emission absorbed by dust. But this becomes difficult because you're often really sensitive to the most extreme galaxies. The source confusion is a problem, and there are few observations with high angular resolution. So you run into issues of that nature. And of course, there are other optical and infrared tracers of the star formation rate, but I am here to talk about radio, so I'm going to move on to that. Okay, so how is radio continuum emission related to star formation rate? Well, the same massive stars that emit primarily in the UV and are connected to the far infrared are the ones that go supernova essentially immediately after they're formed, at least in the context of the universe. And so the cosmic ray electrons that are accelerated in those supernova remnants emit synchrotron radiation. And so in principle, that's how it's connected to the star formation rate. But importantly, this was confirmed empirically through the far infrared radio correlation, which is shown here. It's this really tight correlation between the far infrared and radio luminosities of a galaxy. So I want to sell you on all the ways in which radio observations of star formation are wonderful. A big one is that it's completely unbiased by dust, something you don't have to worry about. And this becomes more of an advantage if you're looking at higher redshifts where our dust models are more uncertain and just the general dust properties, we don't know much about them. And importantly, it traces recent star formation. If it didn't blow up, we don't see it, which means we're really only probing massive stars and don't have to worry about contamination by older stellar populations. Something I'm not going to talk much about today, but with radio interferometry, you can still observe high angular resolution star formation rate measurements, which is something that the far infrared lacks. And then something that isn't as showy, but is a really big advantage is it has a really simple K correction. So that part of the spectrum, the radio regime, is just a very simple power law. So when you're looking at higher redshifts and needing to correct for cosmological effects, it is very simple to do so. So radio sounds great. Why haven't there been many measurements of the star formation history with radio? Well, star-forming galaxies are extremely weak radio sources. And it hasn't really been until like the last decade or so that telescopes have really had the sensitivity in order to detect normal, ordinary galaxies like our, Milky Way progenitor beyond cosmic noon. And you need to do that in order to trace the bulk of star formation buildup in our universe. So what you're seeing here, this is a press release image of the Meerkat Deep 2 field. So the Meerkat telescope in South Africa stared at one point in the sky for about 150 hours or so and made the deepest radio image to date. So just some statistics about the image are shown on the right. One important thing to note is that this is confusion limited, but we are actually going to take advantage of that due to a lot of properties of aperture synthesis imaging that make this a really powerful tool. Okay, so just to kind of like plug the goal of star formation history of the universe, it was named as the top continuum science goal of SKA Mid, and they were going to go about it a bit differently, looking for detecting individual galaxies out beyond cosmic noon. In order to do so, they needed an RMS noise of about 0.05 microjanskis, and to achieve that would have involved staring at one point in the sky for 2,000 hours. So our measly 150 hours, I'm going to show, actually achieves this goal today without having to wait for the SKA to be built. Okay, so we do this primarily through a confusion analysis. This is what allows us to get to such faint flux densities. Talking about confusion, you'll hear a lot about the P of D distribution. I just want to clarify right off the bat that that is really only just a distribution of image pixel values. It's not something super fancy. The D for deflection is meaning from a pen deflection on a chart recorder. So the term is a little bit outdated, but this is astronomy, so it won't change. Anyway, so how does confusion help you probe star formation history? Well, at every point in a radio image, the flux density is the sum of the noiseless source confusion and image noise. And this is where aperture synthesis comes into play, because in an interferometric image, the noise is both uniform across the entire image and it can be extremely Gaussian. So it's much simpler to deconvolve the noise from the noiseless source confusion signal in order to look directly at the contributions of sources. So that noiseless source confusion distribution is sensitive to differential source counts of galaxies. So in principle, you can take a source count model and determine the P of D that would result from this. You can only do this analytically if the source counts follow a power law. So what I did, I developed a simulation that takes in as an input a source count model and spits out a radio image. So below here, I'm showing two postage stamps of the same part of the Deep 2 image, but one is real and one is not. So this is what a P of D distribution looks like. The measured P of D distribution is shown as the black data points here. And then the P of D distribution that was found by fitting the source counts to the observed P of D distribution is in red. So, I mean, that's a pretty good fit. So in that way, we were able to constrain the source counts, which will eventually give us the star formation history of the universe. So these are what the source counts actually look like. The top plot is a more traditional way of presenting them, the Euclidean normalized source counts. The confusion measured source counts are shown as the thicker black line at very faint flux densities. The thinner black lines surrounding them just show the error, 1 sigma errors. Also, the other data points were direct counts from both that same Deep 2 image and NVSS. The most important point, though, out of this plot is if you look at where our Milky Way would have been at a redshift of 4, assuming about 10 times luminosity evolution, it wouldn't appear until very faint flux densities. So it really isn't until now that we have had the sensitivity to detect normal, ordinary disk galaxies past cosmic noon and to be able to measure the assembly of all their stars to give us the universe today. Okay, so how do we actually measure evolution? Well, we kind of have the beginning of the story and the end. The beginning would be the energy density function we measure for the local universe. This is just telling you how much luminosity is in the local universe, and you can relate that to star formation. The end of the story would be those source counts. How can you get from A to B, that is the role of the evolutionary models. And so if you have a local energy density function, you can assume an evolutionary model and predict what that energy density function should be at any given redshift. So you can do that for all redshifts, integrate, and that should give you the source counts that you observe and compare against. So in principle, you know, you can test out different models until you get a source count that matches what you observe. There are primarily two types of evolution that we consider: luminosity evolution and density evolution. So in terms of this plot, a luminosity evolution moves things kind of at a 45-degree angle. Density evolution just moves things up and down. Okay, so, oops, wrong way. In the case of no evolution, the source counts you would get from applying no evolutionary model are shown as the thick blue and red lines for star-forming galaxies and AGN respectively. And the thinner blue lines are showing the contributions to that total source counts from individual gigayears and look-back time. So at the far right, that far right blue curve is showing the contribution to the total source counts from galaxies with look-back times between 0 and 1 gigayears. And then as you go left, it goes from 1 to 2, and so on. And obviously you can see that the case of no evolution is not a good fit. And thinking about density and luminosity evolution, it's clear that in order to match the observations, you need certainly more luminosity evolution, but potentially density evolution as well. Okay, so if you actually try to fit the source counts, this is what you get. You can see that's a pretty good fit. And another thing is that these thinner curves are no longer evenly spaced out. And this is just reflective of the fact that most of the stars in the universe were formed at a narrower time interval, you know, the same cosmic mean we were talking about earlier. The plot on the left is showing the amount of evolution as a function of the age of the universe. So for star-forming galaxies, you only needed pure luminosity evolution. AGN, you had to include a bit of density evolution as well. But one thing to note is that the dashed blue line in that plot is the amount of evolution predicted by the McDowell-Dickinson 2014 model for the star formation history. And obviously they don't match. So what do the radio counts look like if you apply the McDowell-Dickinson evolutionary model? So for star-forming galaxies, you would get out this thick blue curve here, and it doesn't match the counts. And so this is puzzling. And if you think about luminosity and density evolution, it looks like you just need more luminosity evolution in order to get them to match. So we determined that if the far infrared radio correlation is linear, meaning that it's like just a direct proportionality between radio and star formation rate, then you would need about 50% more star formation in order to adjust the McDowell-Dickinson model to match the source counts. So this is, you know, an issue. I mentioned that was assuming kind of that the radio was directly proportional to star formation rate, but the far infrared radio correlation, it turns out, is not linear. So hopefully this will help a little bit. So taking just over 6,000 galaxies in the NDSS with IRAS detections, you can measure the Q parameter, which is just simply the ratio, the logarithmic ratio of the far infrared to radio luminosities. So if you look at that ratio as a function of radioluminosity, you see that it's not constant. So the far infrared radio correlation is not linear. Specifically, the far infrared luminosity is equivalent to the radioluminosity to the 0.85 power. So I've talked about source counts and confusion. I haven't even really talked about star formation rates from radio yet. And the radio continuum is really only a minor tracer of star formation rate. If you were to make an analogy between the far infrared radio correlation, it would be the same as the ratio of the mass of an elephant to the mass of a mouse. So radio is really only a minor contribution. But you can take that Q parameter and determine the far infrared luminosity given a radioluminosity, and then now you have a far infrared luminosity, which is a much more direct conversion to star formation rate. Unfortunately, you still have to assume an INAF. You can't get away from that. But, you know, what can you do? So you can do that for all luminosities and then integrate over everything to get the total star formation rate density at a given redshift. So this is the last slide in my talk, and it's the first time that I'm actually showing you what I promised, which is the star formation history of the universe measured with radio data. So our measurement of this is in the thicker green curve here, shown as a function of the age of the universe. The thinner black curve is that Medallion-Dickinson model, which is, you know, kind of the state of the art currently. The data points are just the UV and IR measurements that went into the Medallion-Dickinson model. So a couple takeaways from this plot is it's not all bad news. We still see a cosmic moon existing at a redshift of about 2. Maybe it's just a bit brighter. There's still a lot more things to work out. The non-linearity of the far infrared radio correlation helped resolve a bit of the gap, but there's still some way to go. So I'm gonna leave this slide here and happy to take any questions now.
Thank you for a very nice, very clear talk. So people can start raising their hand if they have question. I'll start with a question. It's a very simple thing. I'm not very familiar with radio data, but I thought that there are no pixels in radio. So how do you actually, what is exactly this function that you plot? Does it change? Does it depend on the way you reduce the data? Like when you make these maps, you have to choose the number of pixels, right?
Yeah. So radio data is nice in that you're measuring the waves of light, and so you're not actually detecting individual electrons in a CCD pixel. So yeah, you do choose the pixel size when you reduce and image the data. Since that, regardless of the pixel size, it'll still be some sum of the sourceless or the noiseless source confusion and image noise. So it should still give you the same distribution.
Okay. We have a question from Kirsten.
Yeah, hi. Great talk, Allison. Thank you so much. I just had a quick question about your source selection from the NVSS sample for the relationship between star formation rate and radioluminosity. How were they selected, and are they a mix of AGN and star-forming galaxies, or just star-forming galaxies? Yeah,
so really good point. we did disentangle AGN from star-forming galaxies. We used a couple different methods of, radio, far infrared radio correlation. AGN, strong AGN tend to, stick out from that. So that's a selection criteria. We also looked at WISE colors as a way of determining which are star-forming galaxies in AGN, as well as, radio morphology. So we had, 3 or 4 different ways of determining if a galaxy was star-forming or AGN. And that far infrared radio correlation nonlinearity was just from star-forming galaxies.
Next question from Jonathan.
Yeah, Allison, so you talked about how the K correction was simple, and this is all just synchrotron from supernova remnants and things like that, but you cover quite a wide range of redshifts here. So I'm wondering, are there other redshifts at which the contribution from, or what's the next biggest background, I guess? Is it like free from the ISM, or at some redshift there must be some contribution from other stuff? And I'm wondering if you could just say what the worst contribution is.
Yeah, so as you go higher in redshift, the frequency of the emission you're detecting is getting higher. And so then you are starting to get into the regime where you're detecting more free emission than synchrotron. That doesn't happen, at least if you're observing 1.4 gigahertz, that wouldn't be for a redshift of, I don't know, like at least 5, 6, 7, 8. So we wouldn't detect those galaxies pretty much anyway because they'd be so faint. But the thing you would worry about more, I think, is that because it's cosmic ray electrons being accelerated in the supernova remnant, if the galaxy's magnetic fields, the power of that was now about the same as the CMB or less, then you're going to start losing those cosmic rays from the galaxy and not probing the star formation rate as much. But we are predicting more star formation rate, and that would have given you less. So it seems like that's not as much of an issue.
Okay, thanks, and very nice talk.
We have one more question. By the way, I think looking at this plot, you presented this as sort of a discrepancy, but given the uncertainty we have in all these measurements, honestly, to me, 0.2 dex is pretty good agreement. It's not even a factor of 2, right? So
yeah, yeah, partially putting the data points on here, it helps. It's like, oh, okay, maybe it's not as bad as it sounds.
Right. I mean, yeah, I wouldn't. Yeah, there is no single method of measuring the star formation rate which is free from systematics. So you have to compound all the errors in the various methods.
Yeah, for sure.
Okay, so I'll just remind everyone that you can still sign up on the schedule to have a one-on-one meeting with either Fabio or Allison. And let's thank our speakers again. Have a good week, everyone.